Hi, my name is Tador Sonata and I am an IBM Advanced Data Science learner. In this video, I'm going to talk about my dataset preference and why I chose the dataset and what kind of steps I took in my dataset. From starting from reading the dataset, pre-processing dataset, training dataset, evaluating dataset, and finally finding the accuracies and root mean squared error in my different kinds of machine learning models. Let's start with the reading the data. You can see in this code block, I'm reading the data. In DFT, you can see the old features are here written. We had 32 features, including ID and label, which is diagnosis. This data was all about breast cancer and how you can predict if the tumor is good behaviored or bad behaviored. Uh, M is standing for cancerous tumor, which is bad, and B is standing for not cancer. So before I do anything on my dataset, I just want to check if I have any missing values, non-values, because you can't work with the missing values. So I checked for the missing values. I was fortunate that I had any missing values in my dataset. If I had any missing values, I would just simply swap with the mean according to the column of the feature, or just simply drop the column of it or row of the feature. You can see we have no, not a single missing value, which is good. So I checked for the info, data frame info, to see what kind of data types we are working on. So you can see almost all of them is float, which is nice. The data sets had to be in a like numerical values in order to work on them. If you had any strings or objects, any kind of thing like that, we can't work on it. We can't do successful predictions on it. So ID was in integer type of data type, and diagnosis, which is our label, is in object type. So in this column, in this data block, we can see that I'm switching the M and B. Diagnosis had only two values with 1 and 0. 1 is for cancerous and 0 for not cancerous. After switching the values, you can see that diagnoses are starting to become like 1. You can see in here, it was all M, and now it is all 1. The other features, I didn't touch any of it because it was already in a good form for us to use it. After that, I looked up for the correlation with the diagnosis, because high correlation values can help us to predict the model better. Sometimes some features are not so correlated with the level that we are looking for. So if you include that unrelated relevant features with our level, you can fail on the percentages of the accuracy. So I looked up for 0.4 correlation value and up to 1. I take the correlation values from that. If the correlation value was less than 0.4, I didn't take it. I just simply dropped column. It was relevant with the feature. So you can see I also checked for the minus values, because if it's like minus 0.9, minus 0.8, it's highly correlated, but in a symmetric way. I checked for the minus values, but all of the minus values were all already in a really uh, irrelevant values. Like you can see 0.01, 0.008, 0.06. It goes like that. All the minus values were already unrelated with the diagnosis. After the after the correlation table, I just simply draw an heat map with the correlation. You can see how they are correlated. It goes from -1 to 1. Uh, After that, I just simply set labels in here, labels value, which is diagnosis. After choosing my label and my unrelated columns, I drop them. All of them is in there. I dropped all of the columns, and after that, you can see the shape 569 to 21. We had only 21 features to predict anything. In this here, we use train test split from scalar model selection. You can see I printed out all of them: full train data shape, full train label shape. Uh, I used 483 to train them and used 86 to validation and the other 86 to test part. Uh, After that, I was going to evaluate my models. First, I start with the linear regression. In here, you can see the linear regression accuracy is there, and the root mean squared error is there. After that, I looked up for the decision tree classifier. Decision tree classifier validation score was really high, 0.94, which is a good value for this dataset. And another one is you can see the root mean squared of the decision tree, 0.24. I use KNN, key neighbors classifier. You can see all of the parameters I gave, hyperparameters. Chain mean squared error is there, and if you look for the KNN accuracy, 0.9 is less than decision tree. But most successful model was for this dataset was logistic regression with the 0.957. Uh, it's a good accuracy for the predictions, and you can see the RMSE value is 0.24, which is also good for RMSE values. That a good RMSE value should be in between 0.2 to 0.5, which is a good value for that. I also looked up for the XG boost. You can see I'm implementing, I'm training, and accuracy was also good in this kind of it, but not so good as logistic regression. It was 95.25%. In logistic regression, it was 95.7. You can see that here. So I went with the logistic regression accuracy. This is all my work in this dataset. I can predict I can predict up to 0.95%, sorry, 95% for it. I think it's a good value for accuracy, and it's a good value for root mean squared error. I hope that you are also satisfied with these values, because I am satisfied with these values. And thanks for listening. See you.